Hello everyone, we're High Tide Engineering. I'm Linnea Zelskis, this is Janet Yoon, Erica Duran, and Anik Flora, and we are here to present our 4-point channel neighborhood redesign as part of our capstone presentation. Our agenda today includes an introduction, blue space, which is a park with water, green space, which is a park without water, infrastructure, energy considerations, a cost estimate, final design, and a conclusion. So to give a little bit of a background, the 4-point channel neighborhood is in the Seaport District in Boston. It's currently mixed use and contains multiple parking lots. But in the next 100 years, this neighborhood is set to be almost completely underwater. So according to the Living with Water design competition, we must redesign the neighborhood to be able to withstand this sea level rise. And so to give a little more of the background, the datum that our engineering firm has chosen is the NAVD datum. So current high tide elevation is at 4.8 feet, average land elevation is at 9 feet, and high tide in the year 2100 is set to be at 10.8 feet. So once our engineering firm understood where water levels were going to be, we realized that it is our top priority to protect the neighborhood from persistent sea level rise. And this is important because the 2006 existing master plan for the neighborhood that was developed by various landowners and stakeholders does not incorporate sea level rise into their design. So if we do not redesign this neighborhood, as it's already designed, the neighborhood will be almost completely underwater. And additionally, we understand the importance of creating designs that can be replicated in surrounding neighborhoods. Because if surrounding neighborhoods do not implement these flood mitigation techniques, then our neighborhood doesn't stand a chance against seawater flooding. And I've talked a little bit about where the tide is going to be in the year 2100, and now Janet is going to talk about storm tides specifically.
Thank you, Lina. All right, from the NAVD datum, we calculated the average as well as expected increased high tides for the year 2100, shown in blue and green respectively. However, these two high tide levels don't take into account storm surge, which is our main consideration when designing for our neighborhood. Because of this, we will be designing our peak design flow using the annual exceedance probability level of 50% provided by FEMA in order to be conservative with our calculations. So to wrap up our intro, here is the overview of our design. As you can see, we have various green space as well as blue spaces implemented throughout our neighborhood. Towards the top, you can see our blue park, as well as 2 cisterns that we will be building to abut the 4-point channel. Again, here is a brief overview of our design. On the left, you can see the existing conditions, and on the right is our proposed neighborhood. When initially looking at blue space considerations, we thought of canal systems like how you would find in the Netherlands as well as in Venice. But once we looked into our analysis further, we discovered that a canal system wouldn't actually mitigate floodwaters whatsoever. At best case scenario, it would only account for 3 inches of decrease in water level. And this assumes a closed system, which the 4-point channel is not. So what would actually happen is water from the surrounding ocean would flood into the channel, making the 3 inches even more negligible. In order to calculate the amount of water flowing into our system, we modeled our abutting cistern land as broad crested weirs. Using the periods of high tide overflow shown and boxed in red on the graph, we calculated the amount of water that would be flowing into our system. At current land elevations of 9 feet, we would have to accommodate for approximately 0.5 billion cubic feet of water. In order to put this into perspective, the Frog Pond in Boston Commons accommodates for approximately 0.1 million cubic feet of water. Because of the overwhelming amount of water that will be flowing into our system, we decided to increase our cistern land elevation to 13 feet. And next will be Lina with our cistern design.
Thank you, Janet. So the cisterns that Janet has just discussed will be dredged into the 4-point channel as shown here. And the volume of water that Janet has just talked about will be flowing into these cisterns from the channel during storm tides. Now, when we were first designing these cisterns, we made sure to understand any water displacement that would be caused from adding land into the channel. And as Janet discussed, this is an open system, so any displacement of water by filling in this space is negligible. So the way that these cisterns work is water will flow from the channel into the opening between the seawall and the cantilevered park. And once the cistern starts filling up with water, it will be pumped into the blue park that Anik will discuss later. And just to show a brief overview, on the left you see an overview of the system with the cisterns at the top and the blue park in the middle. And on the right you see a cross-section of the pump bringing water from the cistern into the blue park. The pump that HTE Incorporated has chosen is an 80,000 cubic feet per hour axial flow pump that will bring water from the cistern into the blue park. And knowing the volume of water coming in and the flow of the water leaving the cistern, we're able to calculate at what time the blue park will have reached its capacity, the pumps will stop, and the cisterns will hold the remaining amount of water. And this graph here shows that this point occurs at about hour 15. And we would also like to note that design life of pumps is typically a maximum of 50 years. So in the next 50 years, our engineering firm recommends a higher flow capacity pump. And now Anik will talk more about the blue park.
Thank you, Lena. So the blue park is foremost to be used for recreation during the next 50 years. Here you can see a rising dock for recreation that will go up and down with the water level within the blue park. We will be maintaining a water level of 4 to 6 feet within the blue park over the next 50 years. After the next 50 years, the blue park will be used for the extreme storage that Lena and Janet have discussed as the water enters into the cistern and goes into the blue park. So we need to be in control of the volume of water that's in this blue park so that we can allow for maximum storage during these extreme events. The next slide here shows scenario 1. This shows the protection system that we will use for the blue park along the Fort-Point Channel. We've developed this using 2 patented technologies, the self-rising flood barrier from Pre-Sray and the Nordy dock, which is a dock known to have survived Hurricane Sandy. So using fluid mechanics, the self-rising flood barrier will rise with the water level, as shown in scenario 2. This will allow for the protection of the blue park because the water level has begun to rise, coming close to the level of the blue park. And then in scenario 3, you can see that the water level would overtop the wall of the blue park, but is protected by our 2 technologies that we are calling the harbor dock. So everything we've discussed up until now has been for protection of seawater that would come from the Fort-Point Channel. During these extreme events, we also expect an extreme amount of precipitation. Currently, the storm drainage system within this area is limited to within our project area. To determine the amount of water that we will have to deal with in the future, we've used the SCS curve number method to determine a volume of 1 million cubic square feet in the year 2070 for a 10-year storm. The reason we've chosen the year 2070 is because as you go further out into the future with these predictions, your confidence level in these values decreases significantly. So we took 2070 as a good compromise for our data. And our plan for this large amount of water is to use blue space, which can be shown in the blue color on the screen. And everything below the blue line on the screen will outfall into these blue parks. So the bubbles surrounding the drainage structures show where those structures will outfall into the blue parks. Everything above the blue line will outfall into the channel in the existing outfall. The reason we must decrease the amount of volume going to the outfall of the channel is because as the sea level rises in the channel, the outfall capacity will decrease significantly. And now Erica will discuss the best management practices that we've incorporated.
Thank you, Anik. So HTE will be implementing a system of 200 tree boxes throughout the Fort-Point Channel neighborhood. The goal of these tree boxes is to increase stormwater infiltration. They'll do this by collecting the stormwater off of the streets, filtering out pollutants, and redirecting all of that water to the retention ponds that Anik had been talking about earlier. These tree boxes will also provide an aesthetic quality to the neighborhood, which HTE has considered in all of our designs. As Nate pointed out earlier, uncertainty increases as you try to predict storm events later into the century. For this reason, HTE has implemented a variety of emergency technologies and methods into our designs in the case that Boston faces an extreme storm event beyond the capacity of our cisterns in Blue Park. Janet will be talking a little bit more about infrastructure technologies later on, but here you can see how HTE intends to implement green roofing to increase community space, reduce stormwater runoff, and act as an emergency escape route for extreme storm events. The light green represents extensive green roofing, which is a low-cost, low-maintenance vegetation that will decrease runoff by about 65% in these areas. The dark green represents our intensive and semi-intensive green roofing, which means it has an increased substrate depth and more complex biodiversity, which reduces runoff by an average of 85%, allowing us to create a network of community-accessible gardens throughout the Fort Point Channel neighborhood. This network is placed between the buildings most susceptible to flooding, doubling as an escape route during an extreme storm flooding event. In total, we will be introducing 16 acres of green roofing, which will mitigate stormwater runoff by about 15% during a 10-year, 24-hour storm event in 2070, which is about 200,000 cubic feet of water. So this is a SketchUp visual of our green roof network. As you can see, there's a system of bridges between the buildings, which will allow for emergency escape during an extreme storm event. And the building in the top right corner of the screen is a parking garage, which is structurally capable of holding a helicopter to provide supplies or escape during one of these events. This is an example of a prefabricated aluminum bridge which we'll be using between our green roof network. This type of bridge has a high carrying capacity and is very weather resistant. Now Janet is going to talk a little bit more about our infrastructure technologies that we'll be implementing.
Thank you, Erica. So in case floodwaters actually breach our blue and green spaces, we wanted to make sure the rest of the infrastructure at our site would be able to mitigate for any kind of floodwaters. One type of permeable pavement that we will be implementing is interlocking concrete pavers that will be placed along walkways towards individual buildings, while pervious concrete will be implemented along all our sidewalks. Shown on the picture on the right, you can see how much more infiltration permeable pavement will allow for when compared to your traditional asphalt pavement. In terms of individual buildings, we wanted to use a combination of both wet and dry floodproofing. Wet floodproofing involves implementing water-resistant materials and installing them into your buildings. This will allow water to flow through your buildings, making it more resilient while also reducing hydrostatic pressures of floodwaters against the actual building itself. On the other hand, dry floodproofing measures are focused on keeping the water out and sealing the building to prevent any water from seeping in. For individual buildings, we wanted to, one, change utility design so that any mechanical systems as well as electrical systems will be elevated to higher floors of the building in conjunction with implementing wet and dry floodproofing. For new buildings, we will focus on wet floodproofing as opposed to dry floodproofing in order to increase resilience. We will also be implementing floodable garages as well as breakaway first floors in order to alleviate any structural damage from floodwaters. In terms of energy considerations, we will be implementing a heat exchanger technology, which will be located surrounding our cisterns that will be abutting the Fort Point Channel. This energy technology will reduce CO2 emissions by 50,000 pounds annually, as well as decrease heating and cooling costs for the surrounding buildings by up to 30%. In addition, HTE recommends implementing standalone solar street lamps in order to reduce energy consumption of the neighborhood overall. And now back to Erica for cost estimates.
Thank you, Janet. So our total project cost was $93.6 million, and as you can see here, we've broken it down into the different categories that we've talked about today. This total estimated cost is on top of the costs that were already estimated for the master plan that was developed over the last 10 years.
So we've covered a lot of ground today, so we're going to show you a brief overview of the SketchUp that we've put together. So here you can see our two main cisterns along the Fort Point Channel that will be collecting the water that overflows. And here's a close-up view of the park that is cantilevered over the top. And here's the network of green roofs that Erica described with the bridges connecting for an emergency exit route. And now we're going to zoom into the overview of our blue parks that you can see in the back there. And here's our major blue park with our rising dock with a nice little kayak area and our high tide engineering cafe that will rise with the water. And then here's an example of a green space that we will have. Here is a community area with a parking garage below and the tree boxes that Erica has discussed. And so there's a floodable parking garage under normal circumstances and a floodable parking garage during extreme precipitation for any excess flooding. To reiterate our major assumption, for flooding to truly be mitigated, neighboring areas must also implement similar flooding technologies to mitigate their own flooding. Based on the extreme volumes of water that we've predicted to come into this area, high tide engineering has determined the best solution is to first limit the amount of water that enters through the use of the high tide parks, acting as first barriers and then cisterns, then live with the water that does enter through the use of the Blue Park. Based on our data, the Blue Park will not be used frequently for another 50 years. After the next 50 years, the Blue Park is expected to be used more than once a year, and after the year 2100, we expect the Blue Park to be used very often. This allows for the incorporation of water over time. The incorporation of green space from 2% to 34% increases neighborhood enjoyment while decreasing runoff due to precipitation. The improvement of infrastructure and emergency programs increases the resiliency of the neighborhood, allowing us to live with water. Thank you for listening to our presentation.